You attach a file to an email, something important. You hit send. The client thinks for a moment and then comes back with the thing you were waiting for, a small, quiet confirmation, sent, and you move on with your day. But here's a question worth sitting with. How does it know? Your email client said the file was sent, but sent to where? Through what? And how does any piece of software, anywhere on the internet, ever actually know that data arrived? The answer is more interesting than it sounds, because the default answer, the answer baked into the fundamental design of the internet, is that it doesn't know. It can't, not on its own. To understand why, you have to let go of one mental model that most people carry around without realizing it. The idea that the internet is a pipe. A pipe is simple. You put something in one end, it comes out the other. If there's water in the pipe, something happens at the other end. The pipe is honest. The internet is nothing like a pipe. When you send a file, it doesn't travel intact from your machine to the destination. It gets broken apart, chopped into small chunks called packets, each one carrying a fragment of your data. Those packets don't all take the same route. They leave your device and scatter across the network, passing through routers in different cities, sometimes different countries, each one making its own independent journey to the same destination. Some of them will get there, most of them probably, but some won't. A router along the way might be overwhelmed. A link might go down for a fraction of a second. A packet might arrive corrupted, one bit flipped by electrical noise somewhere in a cable. The network doesn't stop to tell you any of this happened. It doesn't issue an error report. It moves the packets it can move, drops the ones it can't, and keeps going. This is called best effort delivery, and it is, deliberately, all the network itself promises. Here's what that means in one sentence. On the internet, the absence of an error message is not the same as success. That's the core problem reliability has to solve. Not how to build a network that never drops a packet. That's impossible, and every engineer who has ever worked on this knows it. The problem is how to build a system that notices when a packet goes missing and does something about it. Think about it this way. You're moving to a new city, and you hire a courier service to deliver 20 boxes. The courier collects your boxes, you sign a form, they leave. 2 weeks later, you're in your new apartment. 18 boxes arrived, 2 didn't. The courier never told you. They weren't asked to keep records. They were asked to move boxes from one place to another, and they moved most of them. That's the job they agreed to do. Now imagine a different courier, one that operates on a different agreement entirely. For every box they deliver, they collect a signature from whoever accepts it and send that signature back to you. If a box doesn't arrive, no signature comes back. The courier waits, then tries again. They keep a log. If something fails, they tell you. That second courier isn't faster. The roads are the same. The trucks are the same. What's different is the agreement, what gets tracked, what gets confirmed, and what happens when something goes wrong. The network underneath your data is the first courier. Reliability is the agreement you layer on top. And here is the part that surprises most people. That agreement doesn't live in the network. The wires and routers carrying your data have no idea whether your file arrived. They don't know what you sent. They don't know what a complete transfer looks like. They forward packets and move on. Reliability lives at the edges, in software running on the 2 devices at either end of a connection, the sender and the receiver, both of them working together using a shared set of rules that turns "I sent something" into "they confirmed it." The sender tracks what it sent. The receiver sends back confirmation for what it received. If confirmation doesn't arrive, the sender tries again. That loop, send, confirm, retry if needed, is the architecture of reliable delivery. Everything built on top of it is an elaboration of that one exchange. There's a question underneath all of this that's worth addressing directly. Why does the internet work this way at all? Why build a network that doesn't guarantee delivery and then solve the guarantee problem separately? Why not design the guarantee in from the beginning? The answer is that the people who built the internet made a deliberate choice. A network that tries to guarantee delivery at the network level becomes enormously complicated. Every router needs to track every packet it touches. Every link needs to maintain state. The whole system becomes fragile because a guarantee is only as strong as its weakest point. And in a global network with millions of components, weak points are everywhere. The design philosophy was different. Build a network that is fast and resilient and makes no promises. Then let the applications at the edges decide what level of assurance they need. If an application needs reliability, it implements it. If it doesn't, a live video stream, a real-time sensor feed, anything where a slightly incomplete picture is better than a delayed one. It can use best effort delivery and accept the trade-offs that come with it. That decision, made in the early days of what would become the internet, shapes everything. Every time your browser loads a page, downloads a file, or sends a request, it's using a protocol that implements a reliability contract on top of a network that was never asked to provide one. The network forwards, the endpoints guarantee. That's the shift this video was building toward. Reliability isn't a property of the infrastructure, it's a property of the conversation, an agreement between two devices that says, we don't stop until we know it arrived. The internet, by design, makes no such promise. Reliability is what you build when a promise is exactly what you need.